Okay. If everything is good, we can start our lection. Do you see the presentation? Can you answer? Okay. So our lection call it the polarization of dielectrics. Polarization types. We will talk about 4 main types of polarization: electron polarization, ionic polarization, orientation, and the space charge polarization. Polarization introductions. So dielectric polarization occurs when a dipole moment is formed is an insulating material because of an external applied electric field. When a current interacts with the dielectric material, the dielectric material will respond with a shift in charge distribution, with the positive charge aligning with the electrical field and the negative charge aligning against it. By taking advantage of this response, important circuit elements such as capacitors can be made. Dielectric polarization is a term given to describe the behavior of material when an external electric field is applied on it. A simple picture can be made using a capacitor as an example. The figure below shows an example of dielectric material in between two conducting parallel plates. The charge in the material will have response to electric field caused by plates. This is the bond charge are the charges that touching the capacitor plates. Will the free charge usually float around the material, but for this case they are aligned with the bound charges. Types of polarization. We have main 4 types of polarization: electronic, ionic, orientation, and space charge polarization. Electronic polarization or induced polarization occurs due to the displacement of positively charged nucleus and negatively charged electrons in opposite direction by an external electric field. It creates a dipole moment in the dielectric. This is called electric polarization. Second, the ionic polarization, which arises due to the displacement of cation and anions in opposite direction, and occurs in ionic solids in the presence of electron field, is called ionic polarization. 3. Orientation polarization. This when an electric field is applied on the electric medium with polar molecules. The electric field tries to align these dipoles along its field direction as shown in figure. Due to this, there is a resistant dipole moment in that material, and this process is called orientation polarization. For space chart intersectional polarization, The space charge polarization occurs due to the diffusion of ions along the field direction, giving rise to distribution of charge in the dielectric. First of all, electronic polarization occurs due to the displacement of positively charged and negatively charged electron in positive direction by external electric field. It creates a dipole moment in the dielectric. This is called electric polarization. The form, the formula is dipole moment when the electric polarization is 1. Here is electron polarizability and electric field strength. It is proportional to volume of atoms and is independent of temperature. And this is the valence electron in covalent bonds in the absence of an applied field. And this is when electric field is applied to a covalent solid. The valence electron is in the covalent bonds are shifted very easily with respond to the positive ionic course. The whole solid becomes polarized due to collective shift in the negative charge distribution of the valence electron. So in conclusion, the electronic polarization is independent of temperature. Electronic polarizations occurs in all dielectric materials. It is proportional to the volume of atoms in the material. Ionic polarization is a mechanism that contributes to the relative permittivity of material. This type of polarization typically occurs in ionic crystal elements such as natriurethium, kaliurethium, lithium-boron. This is no net polarization inside this material in the absence of external electric field because the dipole moment of the negative ions are cancelled out with positive ions. However, when an electric field is applied, the ions become displaced, which leads to an induced polarization. Figure shows displacement of ions when external field, electric external field. The effect of an external electric field on ionic material. The positive charge will flow with the field and the negative charge will flow against the field, causing a net average dipole moment per ion to form. Ionic polarization. Ionic polarization. Let us assume that there is a cation and one anion present each unit cell of ionic crystal natriurethium. When an electric field is applied, let x1 and x2, the distance between positive and negative ions, move from their equilibrium positions. When electric field is applied to the molecule, the positive ions displaced by x1, this one. Two negative sides of electric field, negative ions displaced x2, the positive side of field. The resulting dipole moment per unit volume due to ionic displacement given by like this. This is charge and this is displacement. Next, orientation polarization. When an electric field is applied on the dielectric medium with polar molecules, the dielectric field tries to align these dipoles along its field direction as shown in figure. this one. Due to the resulting dipole moment is that material, and this process is called orientation polarization. This polarization depends on temperature. When the temperature is increased, the dipoles are aligned in random direction. Orientation polarization formula this one, where n number of atoms, p orientation polarization, and this one polarizability. Orientation polarization arises when there is a permanent dipole moment in the material. Materials such as water will have a net permanent dipole moment because the charge distribution of these molecules are skewed. For the example, H chlorine molecule, the chlorine atoms will be given negatively charged, the hydrogen atoms will be positively charged, causing the molecule to be dipolar. The dipolar nature of molecules should cause a dipole moment in the material. However, in the absence of electric field, the dipole moment is cancelled out by thermal negation, resulting in the net zero dipole moment per molecule. When an electric field is applied, however, the molecule will begin to rotate to align the molecules with the field, causing average dipole moment per molecules as shown in figure. The effect of an electric field on typical dipolar molecules. The next polarization is space charge polarization. Occurs when there is an accumulation of charge and interface between two materials or between two regions with materials and external field. This can occur when where there is a compound electric, when there are two connected with the electric material. This is type of electric polarization is different from orientational and ionic polarization because instead of affecting bound positive and negative charges, ionic and covalent bound structures, interfacial polarization also affect free charges as well as. As a resulting interfacial polarization is usually observed in amorphous or polycrystalline solids. Figure shows an example of how free charges can accumulate in a field. The electric field will cause a charge imbalance because of the electric material's insulating properties. However, the mobile charge in the electric will migrate over maintain charge neutrally. This can be causes space charge polarization. This shows how the free positive charge inside the dielectric material towards negative build-up on the right causes by external electrical field. This table shows the comparison of polarization types and typical examples of show the definition examples, temperature depends, reaction time, power loss, frequency range, polarizability. This one is electronic polarization, ionic polarization, orientation polarization, and space charge polarization. This table shows the examples of polarization. For example, argon gas, this is electronic polarization. Water is orientational. Natural crystal is ionic. And the PVC polymer material is orientational polarization. So in conclusion, the separation of negative and positive charges is called polarization. We learned The main types of polarization: electronic polarization, ionic polarization, orientation polarization, phase charge polarization. Next lecture: polarization of ionic crystal with low dielectric constant, another Born theory. Born's theory. Ionic crystals include inorganic classes as well as dielectric containing classes and all other crystalline dielectrics with loose packing of particles in the lattice. Two types occurs in the dielectrics: electronics and ionic polarization. Most ionic crystals have a very complex structure, so it's rather difficult to strictly describe the occurring in them mathematically. For this reason, there is no rigorous theory of the polarization of ionic crystal. However, for ionic crystal with simple structure, the Born theory can be used. Consider the Born theory on binary crystal, natrium, kalium. We place the crystals in an electric field while we assume that local field is equal to external one. Then we have the formula of polarization, and considering that multiple polarization affect this one, and substitute 2 and 1, we take the formula this one. So equating an expression of formula 3, this one, and 4, this one, we take these formulas. Permittivity due to the electron polarization is equal to nu square. Substitute expression 7 nu into 6. We take this one formula, and it gives this formula H. Ions is in the crystal lattice perform chaotic oscillation around the covariant position, while the angular frequency W V of such oscillation is determined by empirical physics. This formula, where K is the coefficient of elastic connection, M is the mass of material point that makes heat wobble. Since thermal vibration are performed by molecule consisting of two ions, each of has its own mass. In this case, in order to use expression, the concept of reduced mass is introduced. In the two ions leads one mass, so we have this formula, where M is the reduced mass. Then from expression 9 is this one formula. From 9 we have the 10 formula. We know from physics that is, if material point moves under action of an elastic force, then the magnitude of force is directly proportional to the magnitude of displacement of the material point, this one, and where delta x is the amount of movement, k, this is coefficient of elastic connection. So if force is the strength of electric field, we have this formula. and from here we have 11 formulas. The induced electrical torque is defined as follows. This one, we have 12 formulas and substitute 12 to 8 to 8, this 8. We have the formula, to take the formula, this one, and we know the AM and M. We have the Born formula. So this Born theory. This is the Born formula. And the example calculating this Born theory, when deriving the Born formula, it was assumed that the field acting on the ions is equal to the external field. This is not entirely true. Therefore, the Born formula gives somewhat an underestimated value in comparison with the actual value of permittivity and is applicable only for crystal with small permittivity, like natrium chloride, lithium dioxide of titanium, for example. Experimentally, it was this value. With Born theory, we have this value. It's a near. How you can see, it's a near. Okay, the next lection. Processing the electrics under the influence of strong electric field. We talked about the processes in the electrics under the influence of strong electric field and the elementary process in gas, avalanche, streamer, and leader. In strong electric fields, new properties appear that limit the use of the electric as electric insulation between electrical conductivity elements. First, insulation gap, a device or elements of devices containing conductive elements with dielectric between them, with an increase in strength of the electric field in any dielectric. After reaching a certain level, a new physical phenomenon arises, an electric breakdown of the gap. Electrical breakdown is the formation of electrical conductivity plasma channel in dielectric between the electrodes of insulating gap and under the action of high voltage. In this case, the dielectric cases to be a dielectric and voltage between the electrodes decreases to zero due to the discharge of charged capacitance of the dielectric through the formed conductive channel. After disconnecting the insulating gap with the liquid or gaseous dielectric from the voltage source, the discharge channel in the liquid and in the gas disappears, and after certain time the voltage can be applied to the device again. The electric insulation of this material is restored. In solid dielectrics, the discharge channel destroyed the material itself, and self-healing does not occur. It is almost impossible to apply voltage to the device after a single breakdown. The voltage at which an electric breakdown of the gap occurs is called the electric strength of gap. It depends on geometry of the clearance and the electric strength of the material. The electric strength of a material is the tension at which the material breakdown occurs. It depends on the material of the dielectric external factors, the quality of dielectric, the type of applied voltage, and the configuration of the electrodes. So, elementary process in gas. This is the avalanche, streamer, and leader. In contrast to weak fields, is strong electric fields characteristic of the orientation of electrical insulating. New phenomena arise associated with the ionization process. The dependence of the current in the gas with increasing voltage has three characteristic sections, like in this figure. So the first is the linear, and the second is the saturation, and the third is the exponential growth. In this region, the electric losses also begin to grow sharply. The reason lies in the appearance of carriers in the gap due to the new mechanism. Impact ionization. Impact ionization is a physical phenomenon of an increase in the number of electrons and ions in the gap due to the collision of electrons with increased energy with natural molecules. So first is the electron avalanche. If the energy over the path length is sufficient, after the first collision an additional one electron and ion appear in the volume. After the second collision, two more electrons and two ions so-called avalanche occurs. The electron avalanche exponential growth of number of charge carriers in the gap from the cation to the anode due to the impact ionization of molecules by electron. This is with this formula. The coefficient alpha, this is the called impact ionization coefficient. It is determined by the donor-acceptor properties of liquid molecules and depends on the mean free path and sharply depends on the field strength. For example, the air is 18 at 30 kilovolts centimeters. Since an avalanche is not breakdown, it is necessary that after the passage of the avalanche, an electron appears at the cathode again. After that, a second avalanche occurs, then another avalanche. An independent multi-avalanche discharge appears. Since the impact ionization coefficient depends on the field strength, the mean free path and consequently the pressure from the condition of independence, it is possible to obtain the dependence of the discharge voltage on external factors. This is called Paschen law, or another form, this formula. So here P is the pressure in the gas, D is the interelectrode gap. Note that the breakdown voltage depends on the product P and D, decreasing the gap but increasing the pressure. We obtain the same dielectric strength of the gas gaps. So what time? Okay. The next is the streamer. In reality, Paschen law is fulfilled at not very high pressures, less than 1 atom, and with small gaps, less than 1 millimeter. In large intervals at normal and elevated pressure, the breakdown mechanism charges. The fact is that as the avalanche lengthens and the number of carriers increases, the charge near the front of the developing avalanche increases. The electric field strength also increases more and more, and the certain intensity that this charge may propagate, particularly without the participation of electrodes, due to the high tension. The called avalanche streamer transition occurs. The transition of discharge from the multi-avalanche form to the streamer form. So streamer is a propagation at high speed in the gap between the conducting luminous plasma local formation. Propagation due to phenomena known as the fast ionization wave, plasma column, and heat with active zone. Produce multiple electron avalanche, replace with the single effect avalanche. Electrons from avalanche neutralize heat. Avalanche becomes new streamer heat. Okay, we need to relax. We have a time. We will continue our relations. Okay. So next process is a leader. Leader as the gap lengthens for the four long gaps. Repeated streamer may appear in the wake of the first streamer. This is because where the streamer passes, the gas heats up, the gas density decreases, and its electric strength decreases. A new streamer with the additional heating can appear and spread in the streamer wake. As a result of local increase in temperature, thermal ionization begins in it, and the electrical conductivity increases by a value higher than transition from the dielectric state to the conducting state. The emergent structure, the leader, is equivalent to the advancement of the electrode in the form of gap or form of tip deep into the gap, which facilitates the breakdown of long gaps. This type breakdown is realized in power lines. So the figure shows a sketch of breakdown voltage sphere to plane distance determined by different stages of development. This is the streamer inset. This area is the propagation, and in this area we have the leaders propagation. So we conclusion. We have the three elections, learned the polarization of ionic crystal with low dielectric constant, and then knew about the process in dielectric under the influence of strong electric field. Next, we will talk about the practical training. Practical training 1 is intended only for the familiarization with the main definitions and formulas. So practical 1, I will talk about one exercise. It's easy, and from 2 till end of the exercise you should do by you, and take a photo and send me. So one exercise, practical training 2, one exercise. A parallel plate capacitor is filled with an insulating material with a dielectric constant of 2.6. The distance between plates, the capacitor is this one, and find the plate's area if the new capacitors is 3.4 microfarads. So we know in the elections that this is the plates, and we put between plates dielectric material. This is the capacity of is increased by the factors K. If we put the dielectric material, we have constants K. So we need to find the plate's area. The plate's area, that is A. We find the A. In this formula, we find the A and put the values, capacitance, distance between the plates of capacitors, constants, dielectric constants, and permittivity. So we have this value. When we put of value, we have the 29.5 meter square. So the plate's area is 29.5 meter square. The next, practical training 3, the dielectric constant 1 exercise. The dielectric constants of gases, gallium, is 1.00074 at a temperature of 273 Kelvin and a pressure of 98 kilopascal, determining the electric dipole moment P of gallium atoms in uniform electrostatic field with an intensity 14. So, solution. The polarization of gallium. We have in the lecture the polarization formula, this one. On the other hand, with the uniform polarization, we have formula this one. This is dipole moment, the polarization, and the concentration of the gallium atoms. So from the equation determining the gas pressure, we know in physics we know this formula. This K is the Boltzmann constants. So we need to find in this formula concentration. We have this formula, and this concentration we should put here. So we need to find the dipole moment here, dipole moment formula this one, and the polarization we put this formula, and in concentration we put this formula, and when we put the value, these values, we have the 2 point this value. So this is we determine the electric dipole moment of gallium. Practical training 4.1 exercise. If an ionic crystal is subjected to an electric field of 1000 and the resulting polarization is 1.3 centimeter square, calculate the relative permittivity of natrium chloride. So in the exercise we given data, this is electric field, this one, and the permittivity of this one, natrium. We have the polarization. So polarization formula, this is one. We need to find the relative permittivity. This is this one. When we find, we take this formula and put the values of polarization, electric field, and permittivity. We take the 5.86. So in this exercise, the relative permittivity of natrium chloride equate 5.86. Next, practical training 5. A potential difference 2 kV is applied to plates of flat capacitors, the distance between which 1 cm. The capacitor is filled with dielectric with susceptibility. This one is 0.018. Determine the polarization of the dielectric. Solution. The polarization of isotropic dielectric is related to the fields by the relation formula this one. This is the susceptibility, permittivity, and the electric field. This is the polarization. Field strength inside the capacitors. We have this formula. So we will need to find the polarization. Polarization formula, we have this one, and we will put here this one, electric field. So we take this formula and we put the value 2 kilovolts 1 centimeter, and this value we have the 0.14 polarization. So we will find the polarization. So I